All right, let's dive right into this. We've spent a lot of time collecting individual parts, right? We've seen exactly how words become rows of numbers, we've learned to read matrix shapes, and we've established that a dot product essentially measures relatedness. Well, now it's time to actually assemble all those individual parts into the machine itself. You see, the transformer architecture has two distinct halves, an encoder and a decoder. In this explainer, we're taking a guided tour of the encoder. We're going to look at what goes in, what comes out, and the exact path a sentence takes through it. And the simplest way to understand its core purpose is this. The encoder is the half of the transformer that reads an input sentence and turns every single word into a highly context-aware version of itself.
To really grasp how it does this, we have to talk about what a contextualized vector actually is. By definition, it's a word's mathematical representation enriched by the meaning of the surrounding words in a sentence. You can think of the encoder as acting like a really meticulous annotating reader. You hand this reader a sentence where every word is just defined in total isolation. They read the entire thing all at once, and then they go back and add margin notes to each isolated word vector so that those numbers now reflect their specific context within that exact sentence. It's the same words, but with a much, much richer understanding.
And here is a brilliant illustration of why this is absolutely crucial. Take the word bank. If you just convert words to numbers using a basic lookup, the word bank enters the model as the exact same vector in both riverbank and savings bank, simply because it's fundamentally the same word. But obviously, that's nowhere near good enough for a machine to truly understand language. The encoder fixes this by letting the word bank look at its neighbors. It adjusts its final output so that the vector for bank mathematically leans toward water if the word river is sitting nearby, or leans toward money if savings is right next to it.
So, here's the kicker. It is all about the shape of the data going in and coming out. The encoder takes in raw word vectors, evaluates them, and spits out a new set of vectors. It takes in exactly one vector per word, and that vector is a size of 512. And what comes out on the other side? Exactly the same number of words, represented by exactly the same number of vectors at that exact same size of 512. The underlying shape of the data doesn't change at all, it's just beautifully enriched with all that context we just talked about. That enriched 512 number output is the encoder's final product, which is what the decoder eventually consumes.
But wait, before a sentence even enters that main encoder machinery to get its context, it has to go through two vital preparation steps at the very front of the architecture. It's kind of like passengers at a train station. You can't just walk straight onto the train, right? First, you need a ticket, which identifies who you are. This is step 1, input embeddings, where raw text becomes math and every word is converted into its learned 512 number vector. Then you get an assigned seat, which dictates exactly where you belong. This is step 2, positional encoding, where we physically stamp the order onto those numbers. Only then are the words actually ready to board the train.
So why do we need that assigned seat? Well, because the encoder evaluates every single word in a sentence simultaneously, it is completely 100% blind to order. If you swap two words around, the model computes the exact same thing. To fix this, we use that positional encoding, which is a specific vector added to a word to encode its sequence order. Before the words flow into the first block, we absolutely must stamp first word, second word, and third word right onto the data. That is literally the only way the model can distinguish a sentence like "the dog bit the man" from "the man bit the dog."
Okay, so once the words are embedded and securely stamped with their position, they enter the main encoder block itself. And every single block pulses to this very specific two-step rhythm. It has exactly two sublayers. First, it gathers context across all the words, and then second, it digests that context for each word individually. Let's look a bit closer at how this builds.
Step 1 is multi-head self-attention. This is the mechanism where every word looks at every other word in the sentence to pull in the relevant context. I cannot overstate this. This is the single most important idea in the entire transformer architecture. When people say the encoder mixes information between words, this is the exact box where the magic happens. This is the precise moment where our earlier example of the word bank finally looks around and discovers if river or money is sitting nearby, pulling that vital meaning right into its own vector.
A really great way to picture this two-step rhythm is with a simple analogy. Think of the attention mechanism as a highly productive team meeting. Everyone in the room shares information. Everyone hears what's relevant from everybody else, and all that context is mixed together. But you don't actually get the final heavy lifting work done in the meeting itself, do you? That is immediately followed by solo work, which is the feed-forward step. This is where everyone returns to their own desk to quietly process exactly what they just learned, entirely individually. So, discussion first, then individual work. That solo work at the desk is the feed-forward network.
It's a standard neural network that gets applied to each position separately. It takes the vector that the attention step just painstakingly assembled, pumps it up from 512 numbers all the way to 2048 numbers, adds a nonlinear step for some extra processing capacity, and then squishes it right back down to 512. This network gives the model the extra processing muscle needed to fully transform the gathered context, and crucially, it works on each word entirely on its own. There is zero crossword mixing happening here. All of that communication between words already wrapped up back in the attention phase.
Now, what's really interesting here is the wrapper around both of these sublayers. It's a mechanism called add-in norm. Honestly, it might look like a minor architectural detail, but it's the absolute secret to keeping the training completely stable. Every single time a sublayer finishes its work, it undergoes step 1, add, and step 2, norm.
So the add step is a residual connection. Basically, instead of entirely replacing the input with the sublayer's new output, we'll actually think of it more like editing a draft with track changes turned on. We literally add the sublayer's new output back onto its original input. The block never just throws away what it started with. You're layering your new brilliant edits right on top of the draft, but without ever deleting or losing the original text. You preserve that initial signal perfectly.
And the practical payoff for keeping that original draft is absolutely massive. Residual connections are the main defense against the vanishing gradient problem in deep networks. By simply adding the output back to the input, it gives the learning signal a clean, wide-open highway to flow backward during the training process. Without this residual connection, it would be almost impossible to stack these blocks deeply because the training would just completely fall apart and the signal would vanish into thin air. Then, after we add that original signal back, we hit the norm step, which stands for layer normalization. This is the process of rescaling all those numerical values back into a stable range. If the residual connection is keeping your original text and tracking the changes, the normalization step is basically tidying up the formatting afterward. It ensures no single value blows up to infinity or collapses down to 0. It keeps the numbers well behaved so the entire document stays perfectly readable as it moves forward through the many layers of the model.
So attention and feedforward, each securely wrapped in add a norm, make up one complete block. While just one block is undeniably powerful, the real encoder is an assembly line. We're talking about 6 identical blocks stacked sequentially, with one feeding directly into the next.
On this assembly line, even though all 6 blocks share the exact same structure, they each have unique learned weights, so they're all tuned just a little bit differently. As the data moves down this line, the output of block 1 becomes the direct input to block 2, and so on. Early blocks in the stack tend to capture simple, local patterns, while the deeper blocks build on those to capture much longer-range, abstract structures. Each station refines the piece a little further. And remember, this deep stacking is only physically possible because that shape never changes. It is 512 numbers in and 512 numbers out, strictly preserved from start to finish.
Finally, after flowing through all 6 of those identical blocks on the assembly line, gathering context, digesting it, keeping the original signal alive, and normalizing the math, the encoder's job is done. What comes off the end of this line is the fully refined, completely contextualized version of the sentence. This final output is completed once and then carried entirely across the bridge in what we call the handoff. These fully contextualized word vectors will now be repeatedly consulted by the other half of the transformer, the decoder.
We've seen the entire blueprint of the encoder now, start to finish. But in mapping all this out, we deliberately left a little bit of a black box right at the beginning of the entry path. We know the attention mechanism inside the block is completely order blind, right? And we know positional encoding is the specific step that fixes it before the block even begins. But that leaves us with a massive lingering question. If positional encoding stamps order onto the data, how exactly do you inject the complex concept of position into pure numbers without completely destroying the original meaning of the word itself? It is a fascinating mathematical puzzle, and quite frankly, solving it is the only way this entire machine comes to life.